All right, everyone, in this video, we're going to track the orbital view of resonance and correlate that to the skeletal view. This will help to kind of validate why we push arrows in the way that we do. So when we have a negative charge or a lone pair atom adjacent to a pi system, we pushed our arrow from that lone pair to the middle of the bond, forming a pi bond, and then we broke the pi bond that was adjacent. Now, tracking in the orbital view, that lone pair on that carbon atom that's negative is actually existing within a p orbital, and we're using that lone pair to form a pi bond to the adjacent carbon. But as I make that pi bond, I have to break the adjacent pi bond, and we leave that pair of electrons in a p orbital on that carbon atom. That's why we see the 1-3 relative movement. The 1-3 relative movement. It's because we're passing that from p orbital to p orbital. Now that the negative is adjacent to this pi system, what we can do is make a pi bond here and then break the adjacent pi bond. Tracking in the orbital view, we take the lone pair from the adjacent carbon, we make a carbon-carbon pi bond here, and then we have to break that carbon-oxygen pi bond. That would leave a lone pair on the oxygen atom, which is then existing in the p orbital. Please also note that there shouldn't be a hydrogen on that oxygen atom, so just cross that out. That's a typo there. So we're moving in a 1-3 relative fashion. 2 arrows are required to describe the flow because we need to make a pi bond, and then we have to break the adjacent pi bond. Right? Let's now track the skeletal and orbital view of moving a positive across the carbon skeleton. Beginning with the far left structure here, I only need 1 arrow to describe the flow as I have an overall positive structure. I'm going to go from bond to bond. Let's imagine that the carbocation itself has an empty p orbital, and what we're doing is we're shifting over all the pi density there, filling that empty p orbital and making a pi bond. But as a result of that flow, this atom here is giving up a share of electron density, so it's becoming positive. Its p orbital is now empty. And that's exactly why we see the 1-3 relative movement of that positive charge. Now that the positive charge is adjacent to that pi system, we can go from bond to bond, moving the pi density over. That is to say, the pi density is being shifted to fill that empty p orbital. So we're making this pi bond here. And that's going to leave this carbon atom empty as a p orbital. That's now the site of the positive charge. So we see that 1-3 relative movement again. Now that the carbon of positive charge is directly bonded to the nitrogen atom, we could take that lone pair from the nitrogen and fill the empty p orbital. As a result of that flow, the nitrogen is pi bonding to the carbon, and the nitrogen would then take on the positive charge. Okay, there it's only a 1-2 relative movement because the nitrogen is simply filling that empty p orbital and making that pi bond. So the reason why we're going over this is I think that one of the natural kind of challenges as we get into resonance is just having confidence of pushing arrows first and foremost, and then having confidence in where the negative goes or where the positive goes. And I think it's helpful to track that 1-3 relative movement when we're moving across the carbon skeleton with the negative. The negative should always move in a 1-3 relative fashion. The positive charge will also move in a 1-3 relative fashion as we move across the carbon skeleton. But when we have that lone pair atom adjacent to the carbon of positive charge, as we fill that, there's only a 1-2 relative movement. All right? And for now, we're going to skip over radical resonance. Again, we'll cover that towards the end of the course when we go through radicals as a chapter topic. So take whatever time you need to fully ingrain this in terms of tracking the skeletal and orbital view. I personally find that's helpful to validate why we push the arrows in the way that we do.